As the world becomes increasingly connected, pathogens and diseases are becoming easier to transmit, and pandemics are becoming more likely. Simple coughs and sneezes release hundreds of thousands of germs capable of multiplying and infecting anyone. Exponential globalization, urbanization, climate change, and travel has made the likelihood of a pandemic dramatically increase as more people come into contact with one another and diseases are harder to detect. Titled Disease X, epidemiologists have proposed a hypothetical disease that could wipe out the world population if not properly diagnosed, tracked, and treated. Without adequate preparation for the disease, it could quickly become a reality and inflict irreversible damage. As such, mathematical models have been introduced to simplify the representation of the spread of a disease within a population and predict how it will progress in the future. These technologies allow for health organizations to determine the dangerousness of a disease before it spreads globally, its effects on the population if left untreated, and its curability, allowing for the maintenance and eradication of diseases before they become pandemics. These predictions can be used to assist the allocation of health resources such as hospital space, vaccinations, doctors and specialists, and furthermore, the prevention of diseases themselves occurring. The SIR model depicts the effects of a directly transmittable disease on a population using simple parameters and variables to predict the patterns, outcomes of the disease, and vaccines used to treat it. The model starts with the human population, or population of cells in the body. The variables S, I, and R classify the population into states based on their infection status. For example, if 9 out of 10 people in a population are uninfected, they are susceptible. S. The remaining 1 out of 10 who has the disease is infectious. I. Anyone who has had the infection and survived to become resistant is immune. R. The SIR model can be applied to any pathogens and may vary dependent on whether the pathogen includes an exposed stage, that is, when an individual is infected but not yet contagious, or can be caught again, thus resulting in no resistance phase. The model constructed is unique to the particular scenario. It can also include specifics about adults and children, men and women and how they react, or how the pathogen can be spread. This information is used to create graphs that visualize how quickly people move between different states and how quickly the disease will affect a population. In the case of disease X, if in the population of 7 billion people, 1 billion already infected, and the chance of a pathogen being passed on between 2 people is 80%, the transmission rate per person would be 1.14 times 10 to the power of negative 10. The transmission rate multiplied by the number of people already infected, 1 billion, and those susceptible, 6 billion, then gives the rate of infection, 686 million people per day. This example is assuming that no vaccination is available and everyone who comes into contact with the disease are infected instantaneously. Should a vaccine be introduced, these rates will slow down. For example, a vaccination is introduced, which decreases the transmission rate by 20%. The rate of infection will also decrease to 514 million people per day. As vaccines are introduced and isolation techniques are established, SIR models will depict the decline of disease within a population and ultimately aid the analysis of pathogens within our world. These models are helpful in assisting in the prediction of the effects of a disease on a given population or community. Through SIR models, mathematics can be manipulated to statistically determine the volatility of a pathogen and ultimately has been and will be used to save the world's population from pandemics.